Greetings, Earthlings. This is the video we've all been waiting for so anxiously. This is on tricky algebra, two trickies. Insanely cool fractal substitution, aka the substitution to end all substitutions, part 3. Alright, so this is going to be the last part in the substitution mini-series we have here. And I'm going to start with some general points. So let's take a look on the left. These are the problems we're going to be trying to solve today. The first one is the square root of 1 plus the square root of 1 plus the square root of 1 plus infinitely. You keep doing that. So this is called a nested square root or a nested radical. Here we have 1 plus 1 over, again, an infinite chain. So these look super crazy, and that's why I've called this insanely cool, because it looks really hard and our solution will solve this insanely hard looking problem. Alright, but before we do that, I want to make a point. So we had this excursion into the math and nature and art series. We talked about Fibonacci numbers, fractals, chaos 3, all sorts of stuff. In particular, the fractal video, and then the substitution parts 1 and 2, and hopefully all of that's going to come into play in this part 3 video. So I want to make one crucial point, which is in the math and nature and art series, I know a lot of you guys just want to learn the core skills, let's say for school or whatever, but and you may think, hey, that stuff is fun, the math and nature and art excursions videos we had, but it's not directly useful. And this is an example of why actually it might be useful. So it's useful for all sorts of stuff, like you're developing your creativity, but also practical, like concrete things. So was that stuff just a fun distraction? And I want to argue that no, it wasn't. So the fractal stuff, while it may have seemed that it was just like, how's this ever going to come into play in like a real math problem? I'm doing this video for two reasons. A, because this is one of my favorite things in all of math, and I want to show you guys these problems. But B, to show you that something that's just fun, you never know when it may be useful. So don't assume, oh, it's fun and it's not directly useful, so I'll never need it. All right. So that's a little bit of background. So basically, if you're enjoying it, don't worry how it's gonna or when it's gonna become useful. All right. So we could just jump in and I could give you guys a solution to these, but I want to encourage you guys to do this with all sorts of problems. So if I'd never seen these, the first thing I'd want to know is, should I waste my time on this? Assuming you want to solve this even, should I waste my time on it? So let's get a feel first. So this is what I'll refer to this as playing with the problem. So let's just play around these a little bit to see, is this worth our time? So how do we get a feel for these problems? Will they blow up? So what do I mean by that? There's an infinite amount of stuff, so one response might be, well, like you keep on adding stuff, so it's just going to be infinity. So why even bother? The answer should be an infinite. We keep adding more and more stuff. On the other side, we keep shrinking it more and more because we're adding more and more ones, but we're taking more and more square roots of the whole thing. So while there's an infinite amount of contributions, their contribution is smaller and smaller. So we have two forces going on. Who's going to win? These extra ones or the square roots? Or will it be some sort of like tie or balance? So that's kind of the thing we want to think about. Same thing here. On the one hand, we're adding more and more terms, but on the other hand, we're dividing more and more times. So that's an interesting thing to think about. How might you play with that? You could try looking at a smaller version of the problem. So let's just take square root of 1. Well, that's just 1, right? Next, let's just pretend this next part's not here. So the square root of 1 is still 1, so we're just going to evaluate the first two. So 1 plus 1 is 2. The square root of 2 is approximately 1.4. Now, let's try another one. So we'll go 3 in this time. So that'll be just square root of 1 is 1, plus 1 is 2. Square root of 2 is about 1.4. Add that to 1, that's about 2.4. The square root of 2.4 is going to be about 1.5, between 1.5 and 1.6. How do I know that? Because 15 squared is 225, so that would be 2.25, and 16 squared is 2.56, or 256. All right, so we can keep doing this, and in fact, if you have a calculator, you might want to do this like maybe 5 or 10 terms out to get a feel for it. So notice this kind of jumped, but then the jump decreased. So maybe this decrease is going to keep happening, but maybe it gets so small that we're going to converge to a number. So this is not related just to this problem. So whenever you see a problem that looks insanely hard, maybe just play around with it, pick a small case. Just looking at these numbers, it doesn't tell me much. So again, you would want to play a little more, but it suggests, look, it's not exploding too fast. So my prediction is it's not gonna, I happen to know the answer to these problems, but I don't think it's gonna blow up too much. It looks like it's gonna sort of slow down and probably get close to a number. So that tells us it's worth solving these problems. All right, how do we solve them? This is one of my favorite things in all of math. So think back to the fractal videos where we had, let's say, this Sierpinski triangle or Sierpinski gasket, and we chop it up into these infinite triangles, and you can keep doing this as many times as you want. All right, so these are supposed to be triangles. My diagram's not great. What was the whole point? One of the themes in that fractal video was self-similarity at various scales. So for example, if we zoom in, let me use a different marker. If we zoom into this upper equilateral triangle, remember we're doing this an infinite amount of times. I've only shown you a few iterations. If we blow that up, it'll look exactly like the original diagram. So there's no difference. So we're going to use that idea here. So this is going to be a substitution of epic proportions. So we're trying to solve this. So step one, we know from parts 1 and 2 is let's give this a variable. So we're going to call this, let's say, x. Here's the key question. Can we find something inside of itself that is also an x? So you could say, well, just the 1, that's not an x. But let's say, what about like this part? That is the same thing. So if I circle, let me circle this properly. We take this part right here. If we were to magnify this to be the same size as the original problem, that is also an x. That looks exactly what we're trying to solve. It's the square root of 1 plus the square root of 1 in an infinite amount of times. That's the key idea. So we've set it equal to a variable, but we're going to substitute within itself. So this is going to be the square root of 1 plus, and this may not look very exciting, but the realization to make this part an x, to me, is mind-blowing. This is amazing stuff right here. It's very powerful. So what we've done is taken an infinite thing that's really hard to even calculate, think about, and because we've already defined one of the infinite things, we can set sort of one infinite thing against itself. So we're leveraging, you can only fight infinity with other infinities. That's what we're doing. All right. So, and from here on, it's just going to be the algebra skills we've seen. But this is the beautiful part. So let's solve this one real quick. We'll square both sides. You can rearrange it to get your favorite quadratic equation. And then you could use the quadratic form. This is not going to factor, so this would be the quadratic formula. So negative b plus or minus square root of b squared minus 4ac all over 2a. So let's see what that gives us. So that'll be 1 plus or minus b squared. That'll be 1 minus 4ac. So if you're not following what I'm doing here, you should go back, review the quadratic equation videos. Minus 4ac, so that's going to be plus 4, because that's a double negative with that one, all over 2. All right, so that's going to be square root of 5. So we're going to get two answers. We're just going to pick the plus and not the minus because this looks positive. The fact that we squared it introduced extra answers. All right, so now funny thing is, this is not just some random number. If you guys remember, this happens to be, if I did this correctly, the golden ratio. So square root of 5 is let's say 2.2 something. So that's about 3.2. Divided by 2 is about 1.6. And if you remember, the golden ratio is 1.618, whatever. So that is your golden ratio. Now, as we're going to go through these three, well, most of these. For number 5, these are things for you guys to do on your own. So for number 5, I want you to think about, is this an accident that this sort of process gave us the golden ratio? So let's do the next one. So hopefully you guys already see the idea here. Well, first thing, we're going to give it a variable. And now, do we see the thing inside of itself? You might think, well, okay, this is the thing right here, but that would be slightly incorrect because we're starting with a 1 plus. So technically, where the thing restarts is from here. You got to make sure that you don't just arbitrarily say, oh, there's some infinite bunch. The infinite bunch we're substituting has to be exactly the same looking as the original. So now we have 1 plus 1 over the original problem. This is the key insight. All right, and now to solve this will be straightforward algebra. Multiply through by x. So that turns into an x. That's going to be a 1. That's going to be an x squared. We can move everything over. And if you solve this, get a load of this. This is the same quadratic equation we just got for that. So I'm not even going to solve that. You're going to get the golden ratio again. So that's one of the other math in nature and art. We talk about Fibonacci numbers, golden ratio. So what is it about these problems that's giving us the golden ratio all the time? I'm going to let you guys think about that. It's okay if you can't figure it out. Just even thinking about that is worthwhile. Can you maybe relate this to plants growing and somehow some additional contribution that's like maybe a tree? You have an original tree, but the things keep getting smaller and smaller, the leaves and the branches. So you keep adding more leaves and branches, but it keeps getting smaller. So that's just a little bit of a hint to, I don't know, maybe that's way off. Just think about it. All right, finally, so now you guys think you're pros at this. Let me just throw a little bit of a curveball. So this looks like one of these sorts of problems, so let's try to solve it again. We're going to set it equal to x. And now we have to figure out where is the original problem. So you can't just circle this part because it starts with a 3. So the original problem started with a 2. So we'd have to substitute that part right there with itself. So we have square root of 2 plus the square root of 3 plus x is x. So we could square it once to get rid of that square root. Now we could square it again. So I'm not even going to solve this because this is busy work at this point. The point of this is not even to solve it. I mean, you're going to get a 4th degree equation, so it's going to be a little ugly. So I don't care much about that. The idea is, I mean, if you plug this into a calculator, there's ways of solving this. That's all I want to just convey. So if you see this infinite mess of a problem, there's nice ways of solving this. So this is not an official term. I like to call it the fractal substitution because it's taking this infinite thing in a fractal inspired way and substituting it. All right. So I'm going to wrap that meat portion of the video up. So these are things for you guys. So number 4, make up your own problems. Like these, harder, play around. You might have discovered things that go beyond what we've seen here. Also, check out the description of the video. There'll be at least one link, maybe more, to some other stuff that will help get your ideas flowing. One of my favorite things is to think about number 5. So why did both of these give us the golden ratio? So you might want to give that a lot of thought. All right, number 6. We're coming to a close in the, so just to remind you guys, chapter 1 in this Art of Math series was number theory, which dealt with arithmetic, LCM, GCF, least common multiple, greatest common factor, exponents, all sorts of basically just working with numbers. That's hence number theory. Next, what we've been doing in this chapter 2, the second chapter, has been algebra, with some interruptions for math and nature and art and other things. But the next big chapter we're going to go into is geometry. So before we go into that, we're coming to a close. There's going to be one more video on this, just as an application of this to another problem that's, well, these look cool, but they're kind of toy problems. So the application will be to like a more realistic problem. And that's going to wrap up our algebra chapter. So as we come to a close, I want to encourage you guys to reflect on some themes that we've seen. So what are some of the themes? Rather than viewing these videos as isolated techniques, I want you guys to focus on themes. So some themes are focusing on the process, the elegance of solutions, not just getting some ugly solution, thinking, and exploration. So there's many more, but the point is I want you guys to be learning good habits and not just like, here's how you do this problem. All right, so abstract, see if you can go through the series, take a look at some videos and abstract. What are some of these, you know, like why is Ilya getting some of these right? Well, how does he, like, what is it about his style that's conducive to doing these? Okay, so that's one thing. So I want to wrap up with a terrible joke. So What kind of tree does a mathematician climb? A geometry. All right, so that's just for our next chapter. So there'll be one video before we get into geometry, and coming very soon we'll be diving into geometry, and I'll see you guys there. I hope you enjoyed this video. I know I've been hyping up and talking about how we're going to apply this in fractals, so maybe I overhyped it. I hope I didn't overhype it, but I really like it. So I'll see you guys in the next few videos.